meeting is being recorded.
So hello everyone. So welcome to the virtual seminar on geometry with symmetry. So it's a pleasure to have David González from the Universidad Politécnica de Madrid, the Polytechnical University of Madrid in Spain, speaking this week. So he will talk about Ricci flow preserves positive curvature on homogeneous spaces. So thank you, David, for giving a talk in the seminar.
Yeah, thanks, Fernando. And thanks to the rest of the organizers. I think this seminar is a very good contribution to the field. In fact, I will mention some of the previous talks. And also thanks to the audience for your time. Yeah, so this is joint work with Jason DeVito and Masoumeh Zarei. The theorem is the title. So the goal of this talk is to give some context to it and an idea of the proof. So the work is essentially done. We hope to put it in the archive soon. Feel free to ask questions anytime. Unfortunately, I'm not an expert on Ricci flow, so I come from the positive curvature world. So you can feel free also to make corrections if I say anything wrong. So this is the Ricci flow equation that I guess all of you have seen. You can I think of it in two parallel ways. So on the left you have like a space whose shape, whose metric evolves in according to this equation. So this picture I took it from Wikipedia. And on the other side, we have the space of metrics. This is this calligraphic R of M. And here we have a path, like a curve, right? So in this case where we have a surface, it is easy to draw it. In contrast, the space of metrics is not easy to draw. In general, it has like infinite dimension and so on. So later in the talk, the situation will be the opposite. The manifold will be impossible to draw, but because we will restrict to homogeneous metrics, we will be able to draw the space of metrics and the flow. Okay, so this equation is a very complicated PDE. It is nonlinear. It becomes easier when we are in the homogeneous setting. But anyway, in general, Hamilton, when he introduced this equation, he answered like the first questions when you have an equation. So there is existence of solutions and uniqueness. So from this year when Hamilton introduced this flow, it has been a very active field of research. So there are many things to look at, like the time of existence. This has to do with ancient and immortal solutions, special solutions like Einstein manifolds, Ricci solitons. Also, what happens with the flow when one arrives at a singularity. And what I'm interested in, this talk is about, is evolution of curvature. Okay. So I guess the idea of the Ricci flow, or the hope, is that you start with something you don't know much about, and you evolve this metric under the Ricci flow, and you end up with something you can recognize. So a way of give me a second. I don't know how to. A way to recognize a metric is in terms of curvature, for example. So there is this theorem of tau that if you start with a surface, then the Ricci flow will evolve it to a surface with constant Gaussian curvature, right? In the convergence sense. So if you look at this picture, well, you have the idea that this path is reaching the subset of constant Gaussian curvature metrics. And we have a classification of constant of surfaces with constant curvature. So this is something we recognize, we know of. And in higher dimensions, we have this notion of sectional curvature. And when it is constant, we get something that we can recognize. So these are the space forms, so quotients of spheres, or the sphere itself in the simply connected case. So I want to highlight 3 theorems which do this. So Hamilton himself, in this first work, he proved that in dimension 3, if you start with something of positive Ricci, the metric will converge, the flow will converge to a metric of constant curvature. Therefore, it has to be diffeomorphic to a sphere. Right? A theorem in this spirit was then given by Bohm and Wilking, and they proved that if you have this curvature condition called two positive curvature operator, so the sum of the two smallest eigenvalues of the curvature operator is positive, then the metric evolves, converges also to constant curvature. So the manifold again must be diffeomorphic to a sphere or a spherical space form. And then I want to highlight this theorem of Brendel and Schoen. They proved that if you take a manifold, you cross it with R, and you get something called positive isotropic curvature, then this also converges to a spherical space form. So it is diffeomorphic to a sphere. And a consequence, much more famous than this statement, is the sphere theorem, that if you start with a manifold whose sectional curvature goes between 1 and 4, then you get a sphere up to diffeomorphism. Okay, so in these 3 theorems, one of the key ingredients in the proof is to study the evolution of the blue condition that you have in each of the theorems. And it turns out that it is preserved under the Ricci flow. So this means, for example, in the first bullet point, if you start in dimension 3 with something of positive Ricci, all the metrics in the flow have positive Ricci. Okay. So in this context, the question I want to discuss is that given a curvature condition, is it preserved under the flow? And yeah, so as I said, I belong to the positive curvature world. So I'm interested in positive curvature condition. And so maybe the weakest, so there are a lot of curvature conditions, right? Maybe the weakest or one of the weakest is positive scalar. And Hamilton proved that this is preserved in all dimensions. Now, yeah, I drew this picture. So you have the big space of metrics. You have the subset of positive scalar, which I drew connected, but it doesn't need to be connected anyway. If I start with this blue metric here and I run the flow, this path will stay inside this set. Okay. And now there is this much stronger condition called positive curvature operator. So the smallest eigenvalue of the curvature operator is positive. Then Bohm and Wilking proved that this is preserved in all dimensions. So if you see the picture, this is a very small set of metrics, which is empty for most manifolds. And if you run the flow of a metric of this blue point, then you stay inside this set. You don't get out of it. Okay, now in between this weak condition and this super strong condition, there are a lot of conditions. I want to discuss, or well, not discuss, but briefly go over it. Twice n conditions. So n is the dimension of the manifold. So yeah, then We have positive curvature operator, which is stronger than positive sectional, which is stronger than something called positive Ricci K. It is, I mean, if you know it, that's fine. If not, it's just an average of sectional curvatures. So here the K goes between 1 and n. So we have n conditions here. Then we have the classical positive Ricci. Then we have another set of n conditions called K-positive Ricci tensor. So these are n conditions again. And lastly, we have the weakest positive scalar. So in this picture, we would have a lot of subsets, a nested chain of sets. Right, so it turns out that these sets are in general not preserved under the flow. So there are quite some examples in infinitely many dimensions where you start with something with, say, a lot of curvature, so quite close to positive curvature operator, but you lose a lot of curvature along the flow, right? So I know this is a vague statement, but yeah, I want to move to something else. Anyway, here these letters go for Abiev and Nikonorov, and this is Masoumeh, Zarei, and myself. Okay, so the expectation is that most of these conditions in the middle are not preserved under the flow, but one needs to construct examples. Okay, so yeah, this is a slide about positive curvature conditions, but from now on, I want to focus on positive sectional curvature. So for the moment, I will forget about the Ricci flow for a moment and just speak a little bit about manifolds of positive sectional curvature. So yeah, whenever you have a curvature condition or a condition, a manifold, a property, I guess the goal is to classify which manifolds admit and this condition and which manifolds do not. Well, I'm going to restrict to the compact and simply connected case. Okay, so we want a classification, which is known in dimension 2. So we just have the sphere. This is a consequence of the classical Gauss-Bonnet theorem. We do have a classification in dimension 3. We only have the sphere, and this is this goes thanks to Hamilton, precisely using Ricci flow. Now, from dimension 4 on, we don't have a classification. In dimension 4, we have one more example, CP2, but we don't know if there are others. In fact, the next candidate in dimension 4 would be S2 cross S2. And this is the Hopf conjecture, which I would say it's quite famous and remains unsolved. Yeah, so we don't have a classification. So what can we do? Yeah, so I guess we can follow like two lines of research. On the one hand, you construct examples. On the other hand, you construct non-examples. And these two lines hopefully converge to a classification, right? So yeah, what do we know about examples? We just know a few. We know spheres, projective spaces, and a few more which I will mention later. But I mean, if you are not familiar with the field, you just can keep in mind that we know just a few. So what about obstructions? Well, it turns out that we essentially know one, which is due to Gromov. He proved that sectional curvature implies that, yeah, I wrote here a very vague statement. It implies that the cohomology is small or simple in the sense that, okay, for the sphere, you just have cohomology in degrees 0 and n. The rest is trivial. You can have some cohomology in the middle, like it happens for CPN, but it can't be too complicated. And it depends on the dimension. So this is a huge theorem, which gives some non-examples. It gives some manifolds that cannot admit positive sectional. But the state of the field is that for most manifolds, we cannot say if they admit or not a metric of positive curvature. Now, here comes the first recommendation of previous talks in the seminar. So if you want to know more about positive sectional, you can see this talk by Lee. Goes back to 2020. I guess one of the first talks in the seminar. So yeah, you can learn a lot about it there. Okay, so yeah, now we get back to Ricci flow, and so this is the question I want to address. Is positive sectional preserved along the flow? So in dimensions 2 and 3, it is preserved. So again, this was proved by Hamilton in his first paper. And from dimension 4 on, the expectation is that it shouldn't be preserved. So this is the expectation, the conjecture, but one needs to give examples, and that's like the goal of our work, to give examples where positive sectional is not preserved. So yeah, what you need to do to construct an example? Well, you have like two parts. You need to start with an example of positive curvature, and then you need to study the Ricci flow and prove that it evolves to metrics with negative curvature, or planes with negative curvature, right? Okay, so these two parts are quite complicated. So let me review the known examples. So it is really hard to construct an example of positive curvature. We just have a few. So the idea is to work with one of the existing examples. So we have some homogeneous examples. We have the compact rank 1 symmetric spaces, so spheres, projective spaces, and the Cayley plane. Then Berger constructed two spaces. A few years later, Wallach constructed 3 spaces. And then Alof and Wallach constructed an infinite family. So the number here goes for the dimension. And here, the subindex P and K, these are integers that parameterize this infinite family. Okay, so we only know infinitely many of them in dimension 7. Okay, so these are the homogeneous ones. We also have some inhomogeneous examples, which I'm not listing because we will not use them for this work. So Eschenburg constructed an infinite family in dimension 7. Basaikin constructed an infinite family in dimension 13. And then Grove, Verdiani, and Sealer, and independently Derricott constructed an example of homogeneity 1 in dimension 7. Anyway, this is the first part, but the second part is that we need to study the Ricci flow. And to study the Ricci flow, there is this result that the isometry group is preserved along the flow. So in particular, if you start with a homogeneous manifold, then the flow stays homogeneous for all times, right? That's why I want to restrict to these homogeneous examples, because they are easier to work with. Okay, so let me put this full list of spaces up here. Okay, so then for the spaces in the list, one of two things must happen, and only one. So either all metrics of positive curvature, when you run the flow, have positive curvature, so the positive curvature is preserved under the flow for all metrics, or there is at least one metric of positive curvature where you run the flow and it goes outside the positive curvature set. Okay, And the idea is the idea of this work is to study which manifolds satisfy the first thing and which spaces in the list satisfy the second thing. So yeah, first of all, some of these spaces only have metrics of positive curvature, like a homogeneous metrics, right? From now on, when I speak about metrics, I always mean homogeneous. So all metrics have positive curvature. So if you run the flow, you stay in positive curvature. So there's concerning this problem, this question, there's nothing to do. So this belongs to the green class. Now, Bohm and Wilking, like now almost 20 years ago, they found a metric. They found metrics on the 12-dimensional Wallach space where you start with positive curvature and then you lose this property along the flow. So this was the very first example. A few years later, Chung and Wallach found metrics with the same property on the remaining Wallach spaces. So these also belong to the red class. Now, a couple of years ago, myself and Masoumeh, we found metrics on the Berger space and all of Wallach spaces, metrics of positive curvature that lose this property along the flow. And this was the situation at the beginning of this work. So we wanted to complete the list. We wanted to see what happens with the remaining spaces, with namely spheres and projective spaces. And this is the theorem, the title of the talk, and it's that they belong to the green class. So the statement is that if you start with a homogeneous metric of positive curvature on the sphere or the complex projective space, the Ricci flow of it has positive sectional for all positive times. Okay. So yeah, as you can see, this theorem closes this classification, right? It tells you which spaces belong to the red class and to the green class. And this is what we are calling theorem B. I put it up there. So we classify homogeneous spaces in terms of whether positive sectional is preserved under the flow or it is not, because there is a metric which flows outside the set. So I'm not giving the details here, but we also do it for the non-simply connected spaces. It's not very complicated. It's just by inspecting the classification and the construction. Okay. So yeah, I guess one of the consequences of this theorem is that if you want to find a new example of a manifold with a positively curved metric which flows outside the positive curvature set, then this example cannot be homogeneous. It must have a homogeneity at least one, where things are much more complicated. So obviously the homogeneous case is the easiest one. However, it can be done. It has been done. So Renato Betiol and Anusha Krishnan found metrics of homogeneity 1 in dimension 4, where you start with positive curvature and you lose this property under the flow. And yeah, this is the second recommendation for previous talks. So precisely, Anusha gave a talk about this result previously in this seminar. So you can have a look at it if you are interested. Yeah, so a consequence of all these results I have mentioned in the last two slides is that by now we know that the Ricci flow does not preserve positive curvature in dimensions 4, 6, 7, 12, 13, and 24. So again, it is expected that it is not preserved in any dimension, at least 4, but we only know it in 6 dimensions. Okay. Okay, so let me say something about the strategy of the proof. So the idea is that we have a manifold, we have all metrics, the space of all metrics, Rm, and inside we have the space of positive curvature metrics. Again, I draw it connected, but it can be disconnected. So this is a very simple drawing that I did with paint. So, and yeah, so maybe the first simplification in this problem is to the obvious observation that if a metric flows outside this set, then it must cross the boundary by continuity. So there must be a G bar, a purple metric, which flows outside P, or the closure of P, right? It is a bit more involved like this. There is some technical detail behind, but well, I don't want to get into it. But this is essentially the idea. So the point of this observation is that you don't need to look at the whole space of positively curved metrics. You just need to check the metrics in the boundary. Okay, so this is a simplification. And yeah, so the strategy is to look at the boundary of this set, and for each metric decide if it goes outside or it goes inside. And this way you know if positive sectional is preserved or not. Now, in general, for an arbitrary manifold, this is not doable because the spaces of metrics is infinite dimensional. How would you describe the space of positive curvature metrics, the boundary, how do you keep control of curvature? So this is unmanageable, I guess. However, in the homogeneous case, it gets doable because everything reduces to computations in the Euclidean space. So let me say, let me explain how this strategy works in the homogeneous case. Okay, so if we have a homogeneous space, G over H, if using a background metric, a bi-invariant metric in G, we get a splitting of the Lie algebra, where H is the Lie algebra of the group H, and P gets identified with the tangent space. So the whole geometry of the space is encoded in this P. Now, 8, the subgroup 8 acts on this tangent space, on P. This is called the isotropy representation. And this representation splits in sub-representations, K many. And yeah, K is not necessarily in general, it is smaller than the dimension of the manifold. So from now on, to simplify the exposition, I will assume that K is 2. It is like the smallest non-trivial case, because the case equals 1 is quite trivial for this problem. Okay, so in this situation, all homogeneous metrics can be identified with R2. So there's a star here, which means that yeah, maybe not all, but if you assume that these representations P1 and P2 are inequivalent, then this becomes true, and this is my situation. So all homogeneous metrics are of this form. They are of the form GTS. So T and S are two parameters, positive real numbers. So yeah, all the metrics are encoded, can be identified with R2. This plus just means that both coordinates are positive. Okay. Now, if you want to study the Ricci flow, you need to study see how the Ricci tensor looks like. And it is of this form, so see that it is almost the same thing as the metric, but here you have R1 and R2. These are the Ricci eigenvalues. Both depend on the parameters, on T and S, so I didn't write it here, but they depend on T and S. And these are eigenvalues, they are numbers that you can compute using the Lie bracket in the group. In fact, we have formulas. I guess the first place you can look at them, or these formulas were written, is in this paper by Wang and Ziller. And yeah, so this is some numbers that you can compute. Now, if you plug this Ricci flow equation, or maybe you plug this information about the metric and the Ricci tensor in the Ricci flow equation, then the PDE, the very complicated PDE, just becomes an ODE system, because the Ricci flow of a metric Ts, it is also of the form Ts. Now the T and the S are functions. They depend on the time parameter, which I'm calling L, because T is used for the parameter of the family. And this is just an ODE system where we have the derivative of two functions, and it depends on T and S. Okay. And now going back to our problem of whether positive sectional curvature is preserved, we need a description of the space of positively curved metrics, right? So inside this R2, where both coordinates are positive, we need to describe those metrics, the subset of positive curvature. It turns out that in all cases, this subset of positive curvature, I'm calling it calligraphic P, is given by the positive values of a function. So here f is a function from R2 to R. So if f applied to Ts is positive, it means that GTS is positive. It works as that. And the very good news is that this has been done already. So Valiev did it for Wallach spaces. Putman did it for all of Wallach spaces and the Berger space in dimension 13. And Verdiani and Ziller did it for spheres, for crosses. Okay, so this is something we can just use, which is very good. And now we need to determine in this strategy if a metric in the boundary goes outside the set or inside the set. How can we detect that? Well, it is just the sign of a derivative. So we need to take a metric in the boundary of this set P. This means that f evaluated at Ts has to be 0. Then it is in the boundary. And then, of course, we need to compute the derivative. Why? Because if the derivative is of this thing, f applied to the Ricci flow, is positive, that means that when you run the flow, f is growing. And if f is 0 at the beginning and it starts growing, it means that f becomes positive, so we have positive curvature. If instead the sign of the derivative is negative, this means that f starts decreasing, so it becomes negative. So the metrics do not have positive curvature. Okay. Let me see the time. Okay, so let me tell you how we implement this strategy in the case of the Berger space in dimension 13. So the isotropy representation has two summands, which correspond, this P1 corresponds to the vertical, to the fiber of this vibration, and somehow this P2 corresponds to the base of this vibration here, where the Berger space fits in. So really the space of metrics is just R2 with positive coordinates. Then we need to describe the positive curvature set. So this was done by Putman. And so it is the red points you see here for which this function is positive. By the way, I'm switching the variables for the picture. So the horizontal one is S and the vertical one is T, according to the geometrical interpretation. Okay, so we not only need to know the space of positive curvature, but also the boundary, which is this line here, the line T equals to S. Now, it turns out that these all metrics in the boundary are the same, up to scaling. So in terms of whether the flow preserves positive curvature or not, scaling does not affect. So actually, we just have to look at one metric, let's say to the metric 2, 1. And now we need to run the flow. For that, we need the Ricci eigenvalues. So these are formulas. Actually, this has been computed before. You get these numbers in terms of T and S. Then you plug this information into the Ricci flow, and you get this ODE system for the functions T and S. Okay, with this initial condition. And now you need to compute the sign of this derivative of f to see if when you run the flow, it grows and it becomes positive, so you have positive sectional, or it decreases and it becomes negative. So to compute it, we just use the chain rule. So this is the gradient of f, which f is this function. It's very easy. You plug in these two derivatives evaluated at 0. So you just incorporate the 2 and the 1 here. You work out the numbers and you get a minus here. So this is negative, right? So this means that f, the derivative is negative, so f starts decreasing when you run the flow. And this means that you evolve to metrics outside this set, okay? So by continuity, this means that there is a metric inside, close to the boundary metric, that also goes outside. Okay, so that's how you find a metric for which positive curvature is not preserved. Okay, so this is for the Berger space, but I want to say something also about the spheres. So let me review the metrics the homogeneous metrics on crosses. So they were classified by Ziller. And in many of the crosses, we actually don't have any metrics, or I mean, we just have one metric up to scaling, so there's nothing to look at. And we just have metrics like non-trivial metrics where we need to study this problem, which are odd-dimensional spheres and complex projective spaces where the dimension is of this form. Okay. So in the spheres, first we have a two-parameter family, GTS. So TS, again, these metrics are identified with R2. So these metrics are defined using these three Hopf vibrations. So the idea is just that you start with the round metric of curvature 1, and then you scale the fibers by T, and you scale the base by S. So these are the two parameters. Okay. We also have a more complicated family, a 4-parameter family. So again, I mean, using these Hopf vibrations. So here S again denotes the scaling in the base, and X, Y, and Z correspond to scalings in the fiber. Okay. And in the projective spaces, we also have a 2-parameter family using this so-called twistor vibration. Again, T denotes the scaling in the fiber, and S denotes the scaling in the base. Okay, so I want to explain a little bit about this two-parameter family corresponding to the first vibration, the circle one. And then I will also say something about the four-parameter family. Okay. Okay, so about the metrics coming from the circle vibration, the Hopf vibration given by the S1 action, so the so-called Berger metrics. The isotropy representation has two summands. This means that the metrics are identified with R2, where both coordinates are positive. We need to describe the positive curvature set. This was done by Verdiani and Ziller, and they correspond to the positive values of this function f here. For this strategy, we need to look at the boundary of this set, which is this line. But again, all the metrics in this line are the same up to scaling. So it is enough to look at one, because all of them behave in the same way with respect to this problem of preserving positive curvature. So we look at the metric where T is 4/3 and S is 1. So there is just one metric to look at. These Ricci eigenvalues are known. They depend on n, the dimension of the sphere. We plug in this information into the Ricci flow equation, and you get an ODE like this, okay? Where you have this initial condition. And again, we compute the sign of the derivative of f evaluated at the points of the flow. So we use the chain rule. This is the gradient of f. Remember that f is this thing here. This is the ODE equations evaluated at the initial value. And we work out the numbers, and we get a positive one. So this means that the derivative is positive, the function grows, and because we started with the function being 0, the function becomes positive. So we are going inside the positive curvature set. Okay, so here positive curvature is preserved under the flow. Okay. Okay, so maybe I finish with this slide saying something about the four-parameter family, which is way more complicated, actually very technical. The numbers are become ugly and hard to manage, so I will only give the idea. So one good thing for us is that the Ricci flow of this family has already been studied by Sami Spiti, and this is the third and last recommendation of the talk. If you are interested, you can have a look at the talk he gave like 3 years ago. And one of the things he proves is that if you start with a metric like this, then the Ricci flow is of the same form. So it is really a family of metrics which is preserved under the flow. This is non-trivial. Okay, so now one needs to know the subset. So we are on R4, right? Now we are on dimension 4. That's why I cannot draw it. We are in dimension 4. And in this R4, we need to describe the set of metrics of positive curvature. Now, this set is described by not one function, but 9. So 9 functions must be positive. It is like an intersection. So this was proved by Verdiani and Ziller. And yeah, so these are 9 cases that we need to deal with. Okay, still, so the boundary of this set is a three-dimensional subset of R4. It might have corners. Again, up to scaling, a lot of these metrics are the same. So essentially, we just need to deal with a subset of dimension 2. Okay. So we need to look at a lot of metrics. In the two previous cases, the Berger space and Berger metrics on the spheres, we had a 2-parameter family of metrics, but we just have to look at one metric. Now we have a 4-parameter family of metrics. We have to look at a lot of metrics at a subset of dimension 2. Now, for each of these metrics in this 2-dimensional subset, we need to compute the sign of a derivative. That's how we know if the thing goes outside or inside, right? So, yeah, that's the computations we have been doing for the last months. Just to show a couple of things. So, after a change of variables, this is essentially that's why you say the A and B instead of X, Y, Z, and S. But essentially, we are looking at this set. This is the set of metrics, the 2-dimensional set. And we are looking at a lot of functions from this set to R. And we need to determine if they are positive or negative. And so, as I said, the computations can get complicated. So just to show you one of the functions we need to deal with. Okay, so this is a horrible polynomial in 2 variables, A and B. And we need to determine if something like this is positive or it has negative points. So yeah, we use to do this, we use several tools. First of all, the computer. So some of the computations have been done with Maple. For example, maybe you have a polynomial like this, but you can factorize it, and Maple gives you a nice factorization. So instead of deciding if this is positive or not, maybe you have many factors and you can treat each factor independently, and this becomes way easier. As I said, there are a lot of symmetries in these 9 functions, and we do a change of variables. That's why you see A and B here, which simplifies things. We need to study critical points of these functions inside this set. We use tools like resultants, Sturm sequences, and after a lot of computations and checking a lot of things, we are now convinced that indeed positive curvature is preserved along the flow also in this 4-parameter family of metrics on spheres. And yeah, this is all I wanted to say. So yeah, thanks a lot for your time. Thanks.
Thank you very much, David, for this very nice talk, and also thank you for promoting the seminar, and the recommendations. Yes.